advantage of us sitting here and listening to talks for the last several days, and to raise perhaps some questions such as, where should we be headed? And maybe some comments on each other's. For example, there's a lot of similarity. I was really taken by the first time, yours, Barry, and Paul, and then also by Kimberly. You're talking in terms of an optimization. They're talking really, when I come from dynamical systems, they're talking about an optimization with other terms thrown into it. And I was taken by, well, he's not here now, but in terms of bifurcation, you're here, Jay, because you're talking about discrimination, bifurcation, and we heard one of the talks yesterday in terms of bifurcation with the parameters and things. And so there seemed like a lot of similarities. I was just wondering whether Rory's type stuff about indirect reciprocity would affect, you know, because it's not quite in that sense, but in the sense of my neighbors who I'm talking to affects some of these others. I just would like to have a general discussion about thoughts about tying some of these things together. How about you, Terry? Let's start with you.
Well, I actually have a question for Kimberly, and I don't know if Natalia's here, but I was sort of, I guess, struck by, given that both the stuff that that I talked about and that you talked about draw on the 97 paper or chapter of yours with Andrade, and given that that's fundamentally about kind of irregularities in the space, it was. I mean, and that you all were talking about sort of rotational invariance and the need for symmetry break. I mean, it seemed like the one possible source for that kind of thing was there right at the very beginning, back in '97. Is that something you all are less sort of convinced is central these days? Or I guess I'm trying to get a sense of what
the question I tried to
what's
ask
happened. What's happened to that? Sort of what's happened? What sort of over the years? What's happened to that idea?
So you're asking why initially the idea was that there's a fixed set of inner point distances that provides an optimal solution, versus our recent empirical simulation results, which says that under some circumstances any rotation is just as good. Is that the question?
Well, I guess the real question is, given that in the original formulation there was nothing like rotational invariance,
right?
Why, I'm unclear on why the modeling starts from a point where there is.
Okay, well, first of all, so, I don't, okay, can I just
Sure.
extrapolate? Okay, the rotational invariance that we get is under a very different set of circumstances from what you see in the human color space situation. So we have far fewer constraints. When discussing an inner point distance optimization model, like the kind that you and Paul show, for humans, it's built on the assumption that there are some features of the stimulus space as well as the interaction with the observer on that space that serve as constraints that provide a solution. Okay, our simulation results say when you remove those perceptual constraints, and you just put in place a communication type of constraint, the actual location of where the categories come out doesn't matter, but you still get, because you get this rotational invariance of the solutions,
right?
But you still get the relational structure that mirrors that which you see in the optimized human spaces.
In that you get these coherent, contiguous categories that are splotchy, that aren't.
You get connected set
right. Okay.
Distributions of categories. They are, related to each other. In our solution, in the most minimal solution with a normal homogeneous population, the connected set categories were of equal size, and that's something that was predicted in the inner point distance model under very simple, non-constrained assumptions, for just simply from confusion matrix types of implications on the space. And so they're not incompatible with each other. But I think one thing that's interesting, a result that's interesting from the psychophysical literature that relates to this rotational property and the idea of an optimization of space is the following result. And Paul certainly knows this result, a set of results by Boynton and Smallman, where they did some search tasks on how well subjects can perform a search task when you have the search codes being segregated colors in the space. So let's assume that you have the whole perceptual space of colors, and you pick some set that are going to be your search targets. And let's just say they're the basic colors, for example. Let's go with the herring 4 colors, red, green, yellow, blue. They're nicely distributed in the space in almost an equal fashion in some regard, okay? At least conceptually they are. So if you have subjects do a search task with those as the search code, they perform at a certain rate, okay? Now if you make the search task based on colors that are much closer categorically, so now say they're within category search targets, so you have a light pink, a highly saturated red, an orangey red, and so on and so forth, then search performance goes down, okay? So the overarching result that Boynton and Smallman showed in 2 papers is that you can find a set of points in color space that optimize search performance for observers, and those happen to mirror basic color terms. You know, it basic color terms fundamental locations in a space, preserving an inner point distance type of idea. Okay, now the interesting point is the following. It's not so much those canonical points in the space that give you the best search performance, because you can take any rotation of those points for observers. And in particular, observer A may have one kind of rotation that optimizes his search performance, and observer B may have a different rotation that optimizes her search performance. But you still have this relational structure in place that serves them both. So you can have a normative code, which preserves this relational structure, and then you can have individual ones that optimize their search performance. So I think the point that the inner point distance model tried to express is that what may not be so important are these specific places in space, but that you have some kind of structure in the topology of how the categorical regions are kind of distributed to each other. And they have to satisfy some perceptual properties, some communication properties, and so on and so forth. And this is why rotation is possible when you remove constraints, and this is why the structure gets fixed when you put certain constraints on.
Stating, I'll get you in a second, but stating it from a mathematician's perspective. If you recall, the first part of the model, which had this rotation in there, it was based on K similarity.
Yep.
The value of K really gave you the number of categories.
Absolutely.
And the fact that K similarities do not distinguish between anything, it must have this rotation effect. If it didn't have it, then there would be something wrong with the model, with the conclusions. And so therefore, it's a consequence of the fact that the K similarity is agnostic about which chips or which bits. And that's a little bit fits in with some of your rotation that you have through in there. And your, you have your similarities and things like that. It's a little bit, there you're related because you've got that sphere. That's a different bulge in it. And that is what gives a, which makes things not agnostic in terms of which bits. And that is the difference between them, and probably between your first paper in '97. Jay, you were going to say something.
Well, I guess I have a couple of comments. One of them seems kind of obvious, but does sort of link all the bits of the work together, and that is that, you know, part that showed us that extremely weak biases could result in a high degree of consistency over time, and so it seems, you know, plausible to imagine that just the tiniest bit of you know, partial systematicity across individuals and where they tend to have their points of, you know, maximum discriminability and so on would, you know, result in relatively robust results in the end. And you could have a huge amount of noise in that, you could have a huge amount of, you know, individual variability, but you nevertheless find that that tiny bit of constraint would lead you to find these things falling in the right place.
Well, that's kind of the point of the things that we've been doing with post. I guess that is to look at if we, I mean, we don't have a good way of measuring what the priors are because they're contaminated by English speakers, but looking at, if we look at what happens when you have these systems transmitted from person to person, whether those small biases are sufficient to induce systems that like the kinds of things that you find in the wireless.
Okay.
What are you going to tell us? Or raise or question or anything?
Yeah, I personally think this workshop was mind-boggling in the sense that there's so many connections and, you know, different points of view that have been brought in by all these talks, which is still spinning in my mind, which I would like to deepen further. That's for sure. Particularly the work on color. There's new things that I learned here, which like about this rotational symmetry and symmetry breaking of it. I think maybe also I hope that mathematicians have seen some new challenges, in terms of that with these models of agents and populations, and with simple rules that we get this amazing behaviors, and we try to understand what it is. And I was very impressed by Thomas talk, for example, how he has been able to put his some framework of thinking on it, which I didn't know yet. That's my general feeling. It's not a question or an issue, but it's sort of a feeling.
Any comments? As a mathematician, I will tell you the following. I truly enjoy it. I got pages upon pages of notes. And one of my real, something that bugs the hell out of me, you use English, is that there has been a tendency in the social and behavioral sciences when they're moving towards more mathematical tools. It's forcing the behavior and social sciences into the mathematics. And really what you're saying is just the opposite. Let's see if we can force some of the mathematics into the social and behavioral sciences, which is something that I strongly believe. And I had pages of notes of ideas to go back and look at this and look at that, precisely the things you had.
Actually, sort of similar comments to Luke's, in that I learned a lot of different ideas about how to deal with the social behaviors that we do see, and what you can gain by sort of abstracting away from sort of the details of the interactions, and getting at sort of the more the nature, the mathematical nature anyway, things that are tractable with mathematical description. And that's something I'm actually really interested in exploring, because a lot of the focus of what I do is like worrying about sort of the smaller details within. And it's very interesting to sort of see what you can get away from and trying to describe at the more abstract level, especially with language change stuff.
Yeah, one thing I would say is that it has been, at least in my experience, sometimes very difficult to get some of this work through. Because like linguists, they would say, well, this is not about real language. It's about, which is true, it's about...
My dog can do that.
Well, he has a robot dog.
That's another thing. So there seems to be in linguistics, at least, maybe less in psychology, that there's a kind of, they don't want to engage with theoretical models, which, of course, if you make a theoretical model, it's necessarily going to be not natural language that's coming out. You will never see in our simulations English popping up. So this is one problem. And then, of course, on the other side, the mathematicians and the physicists, they have their own, I would say, preconceptions, often about language or about psychological behavior. And they make outrageous criticisms, like I got one, for example, this is a paper on perspective reversal in space, where you talk about left alt E and that kind of thing. And then one reviewer says, well, I typed into Google left alt E, and I didn't get many hits, so this paper cannot be very important. This is, I don't think a linguist would ever say that, because they know that perspective reversal is, or a psychologist. But this is sort of the attitude from the, maybe I don't know who did it, but some mathematician or somebody, right?
The Google sciences.
The Google sciences, right?
Well, I don't know. I don't want to mention the journal to avoid embarrassment to this journal, but so I don't know what we can do, all of us, to create here. You created this kind of openness to the 2 points of view, but I think this is an issue.
have to?
I think it's an important issue, and I think it's a crucial issue that all of us have to address in some sense. Louis and I are trying to do this with the graduate students that are here at UCI. You and I were talking about this in terms of what you're hoping to do at Stanford. It's always true in any area that starts to get more and more mathematical, more models, there's always pushback. It's definitely happened in the 70s in economics. They were just really against it until all of a sudden enough results were forthcoming that people began to realize mathematical modeling and economics had a lot to say. And there's still being a lot of pushback in political science. Political science is starting to show where you can make progress. And so it's something that you have to expect. The question is, as you stated, what can we do? And that's Kimberly.
Kind of a little bit unrelated to the.
Oh, if it's unrelated, I want to get back to Paul.
Okay,
Paul
go
had-
ahead.
Paul.
Well, mine's probably even more unrelated, so.
Okay.
So Tom introduced this really interesting rule for how people should raise their hands in such situations. The rule is if you stick up one finger, it's a continuation, and if you stick up two, it's like a
If
new
we all
topic.
end up, it's normally.
I see.
Yeah, you get one.
Well, I remember when I was a kid,
Yeah.
1 or 2, but it meant something different.
Yeah. You know, can I raise one finger? I had something related to this.
Yeah, I think it's a convention in philosophy, right? So where they have very extended discussions such as that, one finger is to follow on, and then a hand is for the topic.
One finger is what allowed?
To follow up?
Follow up in a whole hand. Oh, it was a whole hand. It wasn't two.
Yeah.
So,
Sort of fun.
just this is a bit of a follow-up. I was struck very much by a couple of things that Partha said in his talk. Right? I mean, he is a mathematician. Obviously, I learned by sitting next to him at dinner last night. You know, his philosophy, as articulated, was, you know, I'm going to constrain myself to those types of models for which I can actually prove theorems, rather than to open my mind to the space of possibilities that I think are perfectly reasonable, but which I just don't have the ability to go in and prove theorems about. And you know, this is kind of the opposite to the approach that I've actually taken in my life. And I often find myself, you know, showing that, you know, I've done 1 million replications of this simulation and the data points fall exactly on this line, you know, and yet somehow it doesn't seem like a respectable demonstration of the truth of my proposition until I go and, you know, find a way of proving a theorem, at least about some kind of special case, you know, in this space. And this is one of the challenges that I think we face in any kinds of really complex areas. People at the Santa Fe Institute much talk about these issues all the time, right? And you know, with this particular group, I would be interested in understanding how people, you know, some of whom have much more math than I do, think about, you know, how best to work between these different kinds of.
Well, one of the things we try to do is have conferences of this type constantly. We have, this is our 5th one this year, where we try to make them definitely interdisciplinary. And one of the reasons is that people coming in with from the same discipline, you're talking technical details. What I loved about all the talks is they were all conceptual, the ones that we had here today, you know, over this weekend. They're very conceptual. Here are the ideas, and that's where you can really understand what's going on and have a transfer of ideas. But secondly, when it's interdisciplinary, you have different beliefs and different assumptions. And then that's where you start having challenges and start making, I mean, in every one of the talks there was at least 1 or 2 challenges,
Yeah.
which were expressed in nice words, but what they were is they were essentially commentaries in terms of different beliefs or different backgrounds and things. How do you get people to work together? I think by talking concepts rather than details, and I think really by trying to get intellectual partnership. Too often, like one person told me, well, you know, I guess what happens in the social sciences is what we should do is, you know, we create the models and then we have a mathematician who will look at it. And I says, no, you're never going to get a mathematician who's worth anything that will go look at it. It's much like the mathematician says, well, here I have this theorem, can you help me with the psychology application for it? It's exactly the
Go
same.
get the data that
And you
shows
would say, well, get out of my office, and so it's not going to happen at all. There has to be really a discussion. And so in other words, he said he's creating models where you can prove theorems. Really, all of us do that in our own field, don't we? We just look at what we have here, we are doing that, and a little bit afraid to move out of there because there's a thing called tenure or promotions or salary increases or everything else. But what it takes is to get some sort of an atmosphere that we're trying to create here, where there's going to be a discussion between both sides, and where, hey, I bet I could create a kind of a model or something else. And it's a little bit what I have going on. Tom, follow up on that?
No, in response to Jay's point, I think the kinds of things that we need to do are, I think, you sort of explore interesting questions through simulations, and then you can try and follow that up by doing the analyses. But part of it depends on what it is that you want to demonstrate by doing the work. If you just want to demonstrate that something's possible, then a simulation can demonstrate that it's possible, right? I think it's more, if you want to sort of get these very general results, that's where theorems are useful. I think there are different kinds of questions that require different kinds of answers.
So is this a necessary outcome?
What?
It seems to me that that's the sort of question that an analytic result can answer. That the outcome that I get is this necessary? Does it follow from first principles rather than from some incidental fact about the nature of the simulation?
Right. The thing is that when you wish to prove a theorem, you're often driven to make further simplifying assumptions, which then limit in certain other ways.
Right.
So the case I was talking to Partha about last night was a case in which I could easily show, all of you, that a Boltzmann machine version of a particular kind of model, that is a model in which the connectionist units take only states 0 and 1, necessarily exhibits a certain pattern of behavior. And then there was another class of models, which was continuous stochastic models, where the units had continuous states but with noise added to them. And I found in simulations that those models, exhibit the same kind of behavior when I was able, every time I ran the simulation. So there's an idealization that I can prove the theorem about, and then there's the more continuous case that I don't know how to prove that theorem about. Tom sort of said something, oh, we could probably do that. And if that's true, then I would benefit from his tools. But it seems like that kind of thing is likely to be true frequently, right? That you there's limiting circumstances.
But you have to limit your range. Yeah. You have to limit your scope in order to get a result analytically.
Make it practical.
Yeah, sure.
I wanted to make 2 comments. The first one is that it is true what Tom was saying, that if you want to show that something is possible, a simulation is enough, but if you want a general result, you have to prove a theorem. But in between the two, there are many ways of performing a simulation and of studying it from a quantitative point of view. For instance, exploring in details in the same simulation which are the roles and the behaviors and the dependencies on all the parameters you introduce. Because in my opinion, this quantitative approach to social sciences, in particular language, could be inspired somehow at physics, where it is not true that everything is proved. A clear example is the replica method in spin glasses. There are weird things going on. For instance, there is a matrix and you perform the limit of the number of elements of the matrix that goes to 0. This makes no sense. Nobody has understood this. But it works, and people goes on working on this. But this apparently weird thing is tested with quantitative analysis, or if you want, massive simulation that show that all the predictions can be true, and what happens if you varies this parameter or this parameter. So there is this this polarization between simulations and proving theorem is as a continuum of
Well, actually, when you're talking about moving parameters, and you're well aware from physics, we think moving parameters are going to have a continuous change. In fact, what you can have is a very chaotic change.
Yeah.
You can have very wild things happening in between.
Exactly.
And that often is the reason why we don't have a mathematical result now. Why we have to do with simulations, because things just blow up. I'll show you very simple examples where things like this happen. Okay, back to you, Paul.
I think it would be, I'd just let the conversation continue, because I don't really, it would not be a contribution, but to this conversation is very high and abstract level, and I think it would be better if they continue.
Rory?
I have sort of related comments.
Louder.
I have sort of comments that's related to some of the discussion that's been going on. One of the things that strikes me about the differences in the approaches that are used in various areas, you see the mathematicians, right, that stay on the hyper-idealized, working with things that they can prove theorems about, right? And then there are other models that some of the psychologists use where they get very detailed, right? And they're interested in trying to capture a very specific phenomenon, right? That they saw empirically or something like this. These seem to me two, on the face of it, very, very radically different approaches to modeling. But I think conferences like this sort of reveal that we might have things to say to each other, right? So the very general results might not be as idealized as might not be so idealized that they're useless in particular circumstances. And likewise, the very detailed modeling might give us an idea of the sorts of details that might matter to the results sort of generally. And so we can sort of, I think there's a productive discussion to be had here in terms of getting a sense in both directions. And I think it's good as a group of us to sort of be ruthless in what methods we use, but also so use simulations sometimes, use whatever tools you have at your disposal, but always keep in mind, or always try to keep an eye on the general connections between the sort of very general analytic frameworks and the sort of specific implementations and modeling.
Mike?
I don't think I got anything for you.
Lewis? You always have something on this. This is something we've talked about a lot.
Well, I think one thing was that the issue that was raised about, like in color terms, where we use the syntactical method for picking out the basic terms. And nevertheless, the things we're interested in is communication. Whether the syntax really matches the communication. In language, it's often divided up into syntax, semantics, and pragmatics. Linguists look at syntax, few look at semantics, philosophers look at semantics, analyze that quite a lot.
Lots of linguists.
Okay, well, you're at Berkeley, yes.
Oh, all over the place.
Okay, so you look at semantics. I was thinking more of like in the theoretical sense, the formal sense. I guess that might be now everywhere too. But pragmatics is a bit harder. When we look at the simulations that we're doing, and we're simulating robots doing things or whatever, the basics is pragmatics, the things that drive evolutionary things. When we look at the dynamics, is on the change, is pragmatics. That's what we measure. It seems like there's a type of problem there, in that we don't understand really how these things are related. That's what I would say.
Comments? Anybody else have a comment? One of the things which I really was struck by today, over the last 3 days over the workshop here, is this is one complex topic. And yet I didn't see any of the tools of complexity theory really being used in here. Multi-scale, there's a lot of multi-scale analysis things going on here, a lot of it going on, particularly when we're talking about how the brain and how the does this get out. And a lot of the topics were multi-scale. And linguistics and things, it wouldn't be hard to figure out, you know, the different scales of what's going on between the community discussions, individual discussions, etc. And I'm just curious, anybody here really looking at, I mean, a lot of your modeling, is there any, anyone here looking at the complexity theory? I mean, you must use some of that, the complexity theory in terms of computing and that. Is there anybody using complexity theory or any of the results from complexity theory to try to put a handle on some of this?
Well, yes, in a model I exposed yesterday, not yet probably, but for instance, you know, the approaches to the easier naming game, we try to use a lot of concepts from statistical mechanics. Now,
Well, you're using statistical mechanics, correct?
yeah, complexity theory is, according to me, a quite vague term. I don't know exactly what you mean by.
Well, they have multi-scale analysis.
Yeah,
For example, when
scaling.
you're talking about statistical mechanics, I saw what you were doing in there because you're doing exactly complexity theory. That's
Can
one
you-
aspect.
I feel somewhat vague about it too, to be perfectly honest. Can you give us a concrete instance of a kind of complexity theory example that? we
All right,
could
I'll give you
hang
one
our hat
which
on?
is, in which I'm doing some analysis, and that is the individual interactions. Excuse me. The individual interactions have, on the micro scale, helped develop health theories and national health and different things like this. So we have on one scale the individual interactions, and then what we're going to do is aggregate the individual to get what happens at the next scale. And what happens at the next scale is not necessarily the same that happens on the individual scale. That's what happens in statistical mechanics and large, and what you were talking about.
So in the examples that I talked about, I gave results for one and infinitely many.
That's right.
But in between, it gets much.
That's right.
Yeah.
And so, what we do is in engineering, nanotechnology. They're looking, you know, they got the little at the nano level that's then has determines the surface material, et cetera, like this. And statistical mechanics is not working there. And what they're doing is they're trying to develop ways of understanding what happens at one level and how it affects the other level. Techniques are being developed. I was just curious whether anybody here is thinking about some. In fact, I thought you were going to talk about that when I read parallel and distributive processing. I thought for sure you were going to be bringing in things.
So there's, okay, well, so to the extent that I'm engaging with this at all, I will bring something that is an issue that people who I talk to think about some, and that is, you know, the connectionist level of abstraction. We always talk about how it's inspired by the brain and everything like that, but you know, real neurons in the brain aren't very much like the continuous units that we use in our networks. And there is a body of work that a variety of people are involved in now, trying to understand. So, you know, what properties that come from the actual spiking neuron models should we import into a reduced description at the higher level to make them better models of what, you know, the actual population is really doing, as opposed to just sort of like scratching our head and saying, well, let's use a logistic function, or let's justify it on the basis of the Bayesian principle. You know, what are the emergent consequences of the actual neural dynamics? And I think this is going to be something where the kind of physics that you were talking about is going to be extremely relevant, right? Because it's going to be hard to prove things about that, perhaps, but there's going to be some obvious emergent results.
Yeah.
Yeah, I also want to emphasize that everything we do is totally inspired by this idea of complex adaptive systems, you know, about the emergence of structure and how the emergent structure influences the behavior of individual elements, kind of grouping, level formation. So this is the foundation. Well, maybe we didn't talk that much about it, but you know, all the ideas coming and also all the dialogues that we're having with biology, for example, are in that level.
Yeah. And if I can say, in this sense, probably what I showed yesterday is also a sign of this approach, because we had the, I don't know if you remember, this emergence of a higher level layer, that was the linguistic one. and on that level there was the agreement. So this was the truly emergent feature in the model.
We got only a couple, I asked the bus shuttle to come a bit earlier, since we're getting through there. I sent the email, and I hope she got the email and ordered it. So I'd like to conclude with a couple of comments. I think we had a very good conference, and I really want to thank, this is the first conference that we've had since I've been director where I've had almost nothing to do with the organizing of it. And I want to thank the two people who really did a lot of the organizing. One of them isn't here, she's with her 2-month-old child, and the other one right here is Kimberly. So I
just want to say that Janet Phelps did far more than I did, so.
Oh, well, that's the second one I
Yeah,
wanted to say.
so-
And Janet Phelps is invaluable. Anything
Yeah.
that goes smoothly is due to Janet.
Yeah.
And
I don't
I would
know if she's
appreciate it if, as you walk by, you just give
Yeah.
her a word of thanks or something like that. She is tremendous. The Institute just plain, like I stated, is the two of us have developed a division of labor. She does all the work, I claim all the credit. And she's absolutely tremendous. Any last comments anybody has or anything like that? I thank you all for coming. Thank you very much.